All right, hello everyone. Welcome back to Physical Geology 1403. Today is lecture 2. We are discussing matter and minerals. That is the second phone dropped today. We'll see how many we get. All right. The question that was put out before I pushed record was, do you have to print off the acknowledgement of resources? If you can sign it digitally, there are some programs that let you do that, like Adobe Acrobat. Feel free, just as long as you get it signed, dated, and then returned to me. And if you've read the acknowledgement of resources, you understand what that is. It's me saying all of the many things that I have given you to succeed in this class. The reason why that's there is a purely cover my butt deal. Because I've had students that, I mean, if you've read the lists, then you know there's like 8 things on that list, things that help you succeed in my class. But in the past, students have failed my class and then gone to my superiors here and said, he didn't give me enough help. And then they come to me and they say, this student is blaming you for their failures and you need to justify your, the way that you taught your course. That happened enough times that I was like, okay, I'm just going to have everyone acknowledge right off the bat what resources there are available so that you can't then blame your failure on me because I give you so much stuff to succeed. Okay? If you don't use it, that's entirely on you. So that's what that acknowledgement of resources means. I offer you tutoring by myself as well as an evening tutor. I have an evening tutor whose hours I actually just got yesterday in an email. So I'll go ahead and share those with all of my classes later on today in an announcement. So if you can't come get tutoring during the day, then you can feel free to come during the evening. Most of the days it looks like she's available between 7 and 10 p.m. over at the LRC, our Learning Resources Center here on campus. Okay. So one way or the other, you should be able to get tutoring from her or from me. Okay. No reason why you shouldn't be able to ask your questions and get help. Most of the time, I imagine it will be from me, and that's totally fine. I love helping you all with these questions. There is no textbook, but there is a text, a digital text. I guess it's technically a textbook, but it's open source. I verified it. It's all good. It's there on the website. There is the website itself, which has resources that I have made specifically for the class. All of the lab materials are on there. Any questions you may have could be answered on there. Just please, if you're struggling, reach out to me. I can't help you if you don't. Okay, I'm going to keep hitting that point over and over throughout the semester. I hope you get comfortable with reaching out to me and asking for help. Or I may be asking each other for help. That works too. Or coming to me as groups if you have the same questions. Any of these options are good. Same is true for my online students, by the way. I know that you are watching this asynchronously. GoReact is supposed to kind of help alleviate that asynchronous gap between you and me. But if you would like to work together in groups, then in the GoReact chat, you can actually coordinate with each other who wants to be in a group. And then if you'd like, I can make a group for you on Blackboard so that you can chat with each other back and forth on Blackboard about projects and the such. You just need to let me know. One person from your group needs to let me know who is in your group and who wants that option, who wants to opt into that group option. I could technically do the same thing for y'all as well. If you wanted to discuss things in your group outside of lab times here in person, I could make a group for you on Blackboard. You just need to let me know that you want it. Cool. Long answer to your question. Any other questions before we get started today? Where's the snack at? Okay, cool. Any other questions? I also have a little baby turtle. He's turtles take torpor a little more seriously. Like I pull him out and he's just kind of like, okay, fine. I take the turtle out and he's like, pretends to be dead. He's just like, it takes him like, and then he's just like a derp for the rest of the day. So I just leave him alone while he's in torpor. He'll wake up and start eating and stuff again here in about a month or so once the temperatures start rising in the building. And then I'll bring him out to play and you guys can see him. He's really cute. He's about that big. I call him Algernon. Okay. No other questions? Then we can begin for the day. I don't think I have any announcements other than you are getting Lab 1 today. And it will be due in 2 weeks. You are getting Lab 2 next week, though. So the last half of Lab 1 will overlap with Lab 2. And the reason why is because Lab 1 is the longest lab. It sets the stage for the labs that come later, which you'll understand more after today. All right. Okay. Shall we begin? No? Oh, no. Okay, well, I'm sorry, but we have to. All right. Today we are learning about matter and minerals. So in that first lecture, we kind of, oh, don't do this already, here we go. We kind of did a macro scale, a wide view of the science of geology in general. Starting with today, we are going to zoom in really far onto the tiniest little aspects of what makes up this earth as a whole that we have studied. Just like a blade of grass is to the comparison of the size of the planet. Today, we're not focusing on the wide view of geology, on formations and mountains and volcanoes. That comes later. Today, we are focusing on, initially, matter. What is matter? Nothing. What's the matter with you? Right? No? Okay, stuff. Explain stuff. What is stuff? Stuff is a weird word. Stuff is a difficult word to quantify. In English, we can stuff stuff in stuff. So it's difficult to use that as a descriptive word. Tell me what matter is a little bit more descriptive. We're in college. Be a little more descriptive. Yes? Anything that has mass. Ooh, how's that for a description? It takes up space. It has mass. It takes up space. Okay. Aylin, Isaiah, Gabriel, Ashton, Trent, Jose, Manuel, Andrew, Samuel, Joe, Miriam, Abigail, although Abby, right? We were going with Abby here and Abigail here. Marquez, yes. Giselle, Anthony, Daisy, that's right, Daisy, Marissa. What is it again? Raymond. Alyssa, Victor, yours fell over, I'm so sorry. What is it? Karina, Abigail, and Claudia. Okay. All right. How are we feeling about these descriptions that we got? Something that has mass and takes up space. Good. Any additions? Okay, matter is kind of the catch-all word that we use to describe the building blocks that form everything. Okay, so particles. These particles include protons, neutrons, and electrons. What do protons, neutrons, and electrons make? Atoms, right? The protons and the neutrons together form what we call a nucleus, and the electrons surround that nucleus. It is the arrangement of protons and neutrons that allows us to differentiate between different elements and variations of those elements. And it is the number of electrons in the outermost valence shell, which we'll talk about more in a minute, that kind of allow us to partition things into what we call a periodic table. Okay. Now, we differentiate. I'll get to that in a moment. Let's talk about electrons first. Okay. Electrons, when I say that electrons zip around in an electron shell, you've heard that term before, an electron shell, right? Or maybe an electron orbit. Okay. So most people, when they hear that term, they tend to think something along the lines of this. Perhaps you've seen a diagram like this explaining an electron orbit before, where they follow the same linear path, circling around in the same way over and over and over. There's just a certain number of them, all following their own unique path. That's not actually what it's like at all, okay? An electron orbit or an electron shell is more like an electron cloud. Looks something like this, where however many electrons you have, they're zipping around, maintaining the exact same distance from that nucleus, but zipping out in what seem to be completely random directions, making a solid outer surface, a shell. For some context, scale context, if I had a nucleus the size of a grain of rice in the middle of this room, on that table in the middle of the room, about where those dinosaurs and other prehistoric animals are on that middle table, then perhaps its electron shell would be about as far out as the walls and ceiling and floor of this room, making a sphere around it. But you could go up to it and knock on it. It would seem solid to you. That's why things have resistance. Solid things, liquid things, gassy things, all of them are matter, made out of matter that can be interacted with other matter. The electron shells in the atoms that make up my skin are interacting with the electron shells that are making up this desk right now. Okay, that's what gives things their substance to interact with each other. They're moving at about 1,360 miles per second, which is why they do appear to be solid, as if they were a solid structure. Instead, it is many tiny things moving that quickly all at the same time. Okay. Now, the atomic number on an element is dictated by what? This number right here. The number of protons in the nucleus. Boom. The number of protons in the nucleus are how we determine elements from each other primarily. Okay. There are 94 natural and 24 synthesized elements. For now, that changes fairly often. When I first started teaching this class 5 years ago, I did have a textbook for the class that had been written several years before that. So right now, it's about a 7-year-old textbook. In that textbook, it said that there were 22 synthesized. Just in the last couple of years, we have synthetically made more elements, and there will be more continually being made. What does synthetic mean? What is a synthetic element? Was created by what? By us. Yes. A synthetic element is one that is made usually in a super collider, and it can only exist, even if it only exists for a picosecond. If we can prove that it existed at all, that's a new element. Okay? If it then just falls apart like a sandcastle, if it dries out too much, it's just gone. It still existed for some period of time, and therefore it is an element that we made, and that's a synthetic element. There are 24 of those, which is pretty cool that we can do that. It's the level of technology we have. Now, protons have a positive charge. Electrons have a negative charge. Neutrons, what sort of charge do you suppose they have? A neutral charge, hence the name neutron, right? So if I have an element that has more protons than electrons, is it going to have a net negative or positive charge?
You said more what? I
apologize. No worries. More protons than electrons.
That's not positive.
Say it louder.
Positive.
Net positive charge, right? You have more positive stuff than negative stuff, right? What if I have more electrons than protons?
Negative.
Negative charge, right, to my particle. What if I have an equal number?
Neutral.
It'll be neutral, okay? A proton and an electron walk into a bar. The proton feels for his wallet and says, I can't find my wallet. Electron says, are you sure? Proton says, I'm positive. Right? I told you I'd tell you bad jokes. Promise there are more coming. You just wait for it. They'll come out of nowhere. Okay? They'll catch you off guard, knock you off your feet. You won't know whether to laugh or cry. Now, we arrange things in this periodic table of elements by a couple of factors. First of all, look at how they are arranged numerically. Here's 1. What does 1 mean?
1.
1 what? Proton in what?
1 electron.
In the nucleus, right? 1 proton in the nucleus. This number has nothing to do with the number of neutrons. Okay? Absolutely nothing. We're not there yet. We're just talking about atomic number. Atomic number is purely the number of protons in the nucleus. Okay? Helium has 2. Lithium, 3. Beryllium, 4. So 1, 2, 3, 4, 5, right? There's another way that we organize these. I'll talk about that in just a moment. It's just another way of looking at that with a darker background. Some people have a hard time seeing things on a light background. So if you have an easier time seeing things on a dark background, that's for you. Okay, now let's talk about the ways that atoms bond with each other. An atomic bond is when one or more atoms are drawn to another to satisfy some requirement. what would possibly need to be satisfied? Do you think an atom is thinking to himself, you know what would be really cool right now? If I could find a hydrogen. They aren't alive. They aren't thinking. There is some physical draw forcing them to be bonded together. Things that can cause bonds to happen include heat and pressure. Those are the two most common ones. Okay? If you think of another natural bonding force, you could think of magnetism as an example here. Magnetism is not what draws elements together to make bonds, but you can think of that as an analog to help you imagine it. Okay? Just like a positive and negative dipole in a magnet are drawn together, two elements that are drawn to each other for other physical reasons will collide with each other and then form that bond, making a compound. Okay? Heat and pressure can make and break bonds depending upon what the parameters of that bond are. There are three different types of bonds that we're going to review. By the way, I'm assuming all of you have taken chemistry at this point. Fundamental chemistry and fundamental physics, really, even if you just took them in high school, or if you took the fundamentals in grade, I don't know where you went to school. I know some schools teach basics in those things. But I have to assume that you have taken the basics. I'm not spending a whole lot of time on it in this class. A lot of you just went, whew, right? I'm assuming that you know the basics. So I'm just brushing over the stuff that you need to know for sure to understand what comes later. Okay? So an ionic bond, a covalent bond, and metallic bonds. Those are the three types of bonds that are relevant to our conversation. Atoms that are bonded to each other needed that bond in the first place because for one reason or another, they were more unstable in their condition before. Therefore, by having achieved that bond, they are now stable, more stable. Okay? The octet rule states that atoms tend to lose, gain, or share electrons until they have 8 valence electrons. I used that word before, valent. Do you remember what valent means, any of you? The outer electron shell. Boom. The valent shell or outermost electron shell is the valence, and that's where the valence electrons reside. Now, atoms want 8 valence electrons. So if I'm an atom that has 1 valence electron, I want 7 more, and I'm going to bond with other elements to satisfy that. Can anyone think of a common example? First of all, before we get to that example, I should share one more piece of information with you that might help you generate an example on your own. Notice how we have our periodic table of elements separated into these columns, right? What do these columns represent? Well, we've got column 1 and 2, and then we've got these ones that are set down here for some reason, right? And then these ones up here that are not offset, upset, they're pushed up. These are inset. Would those be upset? I don't know. But they're up there. So we've got 1, 2, 3, 4, 5, 6, 7, 8 columns. We're ignoring these for now because for reasons. Most of these are metals. I'll talk about metallic bonds in a minute. Okay? But we've got column 1 and 2 through 8. What do you suppose that coincides with? Huh? The number of valence electrons in the outermost shell. Bingo. How many valence electrons do you think these have? 1. What about here?
2, 4, 5.
You get the idea, right? So let's just pick a random element in column 1. How about sodium? Number 11, meaning it has 11 protons, but it's in the first column, meaning it has 1 valence electron. It wants how many? Let's see. Is there another element in column 7 that sodium combines with fairly commonly? Chlorine. Chlorine has 7. It needs 1. Sodium has 1. It needs 7. Match made in heaven. What does sodium and chlorine make?
Salt.
Sodium chloride. Salts. One of the most common bonds that we have on our planet. Okay? Very easy. Matter of fact, it happens in your body all the time. Your sweat and your tears are salty, right? Your body is combining these things with each other, as are many other processes on our planet. Very, very common because they satisfy each other so easily. Sodium and chlorine making that sodium chloride. Okay. When an electron is transferred, we call that an ionic bond. When electrons are shared, it's a covalent bond. And when electrons are shared among all the atoms in a substance, usually requiring it to be the same element, right? That's a metallic bond. Think gold. If I have a mass of gold, it's nothing but gold. All the electrons are being shared between all those atoms of gold. Talk more about that here in a second. That example I just gave of sodium chloride, where you have a sodium with 1 electron and a chlorine with 7, right? Combining to make a sodium chloride. Right now they are net negative or net neutral in their own independent states, right? But by the sodium coming over here and making an ionic bond, meaning that it transfers its electron to the chlorine, now our sodium has lost an electron, making it net positive now. Our chlorine has gained an electron, making it net negative, and they are bonded together to share this nice, satisfactory, valent shell. Opposites attract. Interestingly enough, same with magnets. And just like that, I saved you all tons of time and money on relationship therapy later in life. Okay? It's just natural. Opposites attract. Okay? All right, so that's an ionic bond example. For a covalent bond example, hydrogens. This happens quite often with hydrogens. 2 hydrogen atoms approach each other. Each of them has 1 valence electron. They each want more, right? 7 more ideally, but when you're in an environment that only has hydrogen, hydrogens are just going to bond with each other. H2 will form here, hydrogen gas, okay? H2 is 2 hydrogens that have approached each other, and their valence electrons start being equally attracted to each one of the nuclei until finally you have 2 valence electrons that are just zipping around both nuclei being shared, sharing that same valence shell. That is a covalent bond. Electrons are shared. In a metallic bond, like with that example I gave earlier with gold, and by the way, silver, copper, all these metals are what we call precious metals, right? These are fairly expensive. I'm sure you're all at least in some way aware that gold and silver are expensive metals. Why are they expensive? What gives them that value? Well, they're hard to find now. Why are they hard to find? What has given them so much value for so long that now they are difficult to find? So for a while, they were prized for monetary value. But the amount of gold and silver that was extracted from our planet to make into coinage is vastly smaller than the amount we have used since the development of technology. Why? What do we use gold and silver for? What?
Computer parts.
Why do we use them in computer parts? What do they do?
Conductivity.
Conductivity. That's because of the metallic bond that they have. Metals of the same substance or a close enough substance, if it's an alloy, right, will share electrons with each other interchangeably. Have you ever pulled your toaster plug out of the plug-in and you see that blue zap? Psst. What is that blue zap? Electricity. What is electricity? I'll give you a hint. It's in the first part of the name. They are electrons. That blue zap that you saw for a split second, trillions of electrons that were forming an arc between the metal in your plug and the metal inside your wall socket. You removed it, and now your toaster is not receiving all those electrons, but you saw those electrons just for a split second. Metals conduct electricity, and electricity is just the pure flow of electrons. Metals we use for conduction, and the best ones are like gold. Okay, the best conductors are the most expensive ones typically because we have spent the last hundreds of years extracting them for their conductive properties. Gold is extremely expensive because we've used it for so long for this, and now it's harder and harder to find. And yet it's so useful. You won't open up your smartphone and find a whole lot of gold in there, just a tiny little bit. It's the gold and platinum inside of electronics is a huge part of the reason why they're so expensive. Those rare elements in your smartphone and your laptop. Not much of it. You don't get any ideas. You can't open up a laptop and sell off a significant amount of gold. Okay? But especially since you don't have the ability to extract it, right? But if you were to say, walk onto a military base and look in the guts of an Apache attack helicopter, they use a lot of gold and silver wiring in those things. Why? Because it's a $200 million piece of hardware that you do not want to fail. People's lives depend on it. Potentially the fate of a battle or even a war rests on this piece of machinery. And so you make it out of the best stuff. And so you use gold wiring in the most expensive things, right? It's a big part of the reason why they're so expensive in the first place. So we use these for industrial purposes because of this property, these metallic bonds where electrons are freely shared. Any questions about that? Nothing? Easy to understand? Clear as mud? All right. How we doing? We all staying alive? I haven't put you to sleep yet? All right. Now let's talk about the next thing. We learned about valence shells. We learned about atomic numbers. But what is this number down here?
Mass.
Thank you. Everyone said mass. You know what you didn't say? Weight. I dislike this chart purely for the one reason that they have it labeled as atomic weight. What is the difference between mass and weight?
Weight changes with gravity.
Why does weight change with gravity? What is weight?
It's how it's the force of gravity pulling on you.
It's basically mass times the gravity coefficient of whatever body you are on or near. Okay? So for example, I have the same amount of mass in my body right now, whether I am here or a million light years away on another planet. But if I'm with this certain amount of mass that I have, am standing right here, and then I were to instantly transport to the moon, my weight would change. Why? Because the gravitational pull of the moon is smaller than that of the Earth, and therefore my weight changes even though my mass stays consistent. One of the variables has changed, not both. Okay? So yeah, I would be able to jump higher. I'd feel lighter because I'm not as heavy because gravity's changed. So atomic mass is a more consistent measurement scale than saying something like atomic weight, because weight is only relevant to us here on Earth. Mass is relevant to everywhere in the universe. Okay? So atomic mass. The atomic mass is the total amount of stuff, right, in our element. This includes what? Three things. Protons, electrons, and neutrons. But like we learned earlier, electrons are about 1/2000th the mass of a proton. Fairly negligible. That's why you see 4 decimal places out, 5 decimal places out on a bunch of these, right? I think none of these go further than 5 decimal places. Yeah, but that's a whole bunch of electrons adding on to the end. The whole numbers are largely taken up by the protons and neutrons. So this atomic mass tells us how many protons and neutrons we have in our element. Let's look at some examples here. Where is carbon? Anyone tell me where carbon is? I seem to have lost carbon. Where'd it go? Up on the top? Which column? Okay, it's in column 4. What's its atomic number?
6.
6. Thank you. Now I know where it is. Okay, if it has 6, if its atomic number is 6, then how many protons does it have?
6.
6, but what's its atomic mass?
13. I can't see.
No worries, it's a small number. Anyone over here want to share? Claudia, can you help him out? 12, thank you. Atomic mass is 12. Its atomic number is 6. So how many neutrons are there with those protons? 6. We got 6 protons and 6 neutrons, giving us a total atomic mass of 12. That is carbon. Now, let me share with you that in nature, you can have variations on this. We call those isotopes. Okay? An isotope is an element that has gained or lost neutrons out of or into its nucleus. By the way, what do I get if I change the number of protons in my element?
A different element.
A different element. What do I get if I change the number of electrons in my element? It gains a new electrical charge, right? And that makes it an
Ion.
ion. Bingo. What happens if I change the number of neutrons? An isotope. We call it an isotope when the mass changes because the number of neutrons change. Now, some elements are totally okay with that. Some are not. By okay, I'm kind of anthropomorphizing it a little bit. I apologize. They're okay. They're not okay or unokay with anything. They simply react according to natural laws. But for now, I'm just going to say that they're okay with it. Some things are okay with it and some are not because they don't react or they do. When they do not react, we call it a stable isotope. An example of this, let's go back to our friend carbon. If I were to add a neutron onto a carbon, it would go from what mass? You told me earlier. 12, thank you. It would go to what mass? 13. And now I have an isotope of what we call carbon-13. Carbon-13 doesn't really care that it's carbon-13. It's a stable isotope. Now, interestingly enough, we can use these isotopes to our advantage for studies. I used ratios of carbon-12 and carbon-13 in fossils for my master's thesis to make a paleoclimate reconstruction of Eastern Oregon. I did the same thing with oxygen. Oxygen, where is oxygen on here?
Number 8.
Number 8. And its mass? You might need to help them out again. 15 point what? 9994, right? We round that up to 16 generally, right? So oxygen 16 and oxygen 18 ratios also help with paleoclimate reconstruction. So I used these two versions of stable isotopes to draw conclusions about the past, which is pretty cool. I can tell you more about that later if you'd like. These are stable isotopes. Now, there are unstable isotopes. Now, when an isotope is unstable, it can't handle the fact that it lost a neutron. It's like, no neutron, come back. It falls apart, okay? We call this process of an element falling apart because it is unstable radioactive decay. That's where radiation comes from. Uranium, for example. There are isotopes of uranium that are very unstable. What do we use them for?
Nuclear energy.
Nuclear energy, thank you. That's what the fuel for nuclear reactors is. You take two masses, usually in the form of rods, of unstable uranium or plutonium, or there's other things that you can use as well that are radioactive, but uranium as an example, and you put them close to each other. Each one of these masses of uranium, every element, every isotope of uranium in this mass is blasting electrons and protons and neutrons off of itself in an attempt to reach what? Stability. Ooh, and here is a theme that we're going to see fairly commonly in the class. Things in nature generally seek to find a state of stability. Okay? In the case of unstable elements, they are going to blast particles off themselves until they reach a new stable state. In the case of uranium, where's uranium on my periodic table of elements?
92.
92, with a mass of, help me out again. That's 238. Close enough, okay? It's 238. Uranium-238 is the normal, plain Jane, vanilla version of uranium. The isotope that we use for our nuclear reactors typically is uranium-235. What has changed? How many neutrons have changed? Between 238 and 235? What has happened to 3 of them? Have we gained or lost 3? We've lost 3. And therefore, it now enters a state of instability, and it's going to be blasting stuff off itself until it reaches a new stable element. Eventually, it's going to become lead. Where is lead? Anyone know the symbol for lead?
PB.
PB. Where is PB?
Somewhere on there.
It's somewhere on there. This is very true. Okay, column 4. You see it there? Yeah, 82. Thank you. So we've gone to 82, meaning we've lost how many protons? We've gone from 92 to 82. We've lost how many
10.
protons?
2.
10. We've gone from 235 in the case of the unstable isotope to 207, meaning we've lost how many neutrons? Is it 28?
237 minus 200.
Well, it's 238. Oh, 235. 235 minus 207 is what?
35 minus 207 is 28.
Is 28. But 10 of those were, 10 of that mass were protons. We already discussed. So how many neutrons did we lose?
I mean, 18?
18. Okay, so we lost 10 protons and 18 neutrons, and who knows how many electrons in this process. But finally, after a certain amount of time, which I'll talk about in a moment, we have gone from unstable uranium-235 finally to stable lead-207, and it stops being radioactive, and it is stable, and it is good, and boom, and there. Now, the amount of time that takes can be a while. Matter of fact, this is where we start using isotopes for our advantage in science again. Last time I mentioned how we knew how old the Earth was by dating rocks that came back from the moon. Well, how did we date those things? There's no reference for anything on the moon. Radioactive isotopes. Have you ever heard of something called a half-life? A half-life is the amount of time it takes for a half of the mass of an unstable isotope to decay into its stable daughter isotope, uranium-235 to lead-207, for example. So if I have a dinner plate full of uranium-235, delicious, right? The amount of time it takes for half of that dinner plate full of uranium to decay into lead is called a half-life. Why do we do it in halves? How many times can you divide something in half? How many times can you divide something in half? If I were to take this and divide it in half, and then again,
Infinitely?
and then again, and then again, and again, and again, and again, and again, I could go infinite. I could reduce this piece of paper to a single atom. I can go essentially infinite dividing something in half. So why is this useful? Because I can do this forever, essentially. I can use the amount of unstable isotope versus stable isotope in a substance to determine how many half-lives have passed. And because I know how long those half-lives each take, I can then use that to figure out how old that thing is. For example, for uranium-235 to become lead-207 takes about 307 million years in one half-life. Therefore, if I'm looking at the amount of lead versus uranium-235 in something, and I see that there is a 75 to 25 ratio, I know 2 half-lives have passed. The first half-life divided the uranium in half. I had 50-50. The second half-life divided it again. I had 75-25. A third half-life would divide that 25 again, and I'd have a 12.5 to whatever the rest is ratio, right? You following me? This is how we use half-lives. This is how we know how old the Earth is, by the half-lives that have passed in certain substances that have been around since the beginning of the Earth, like what's on the moon. Isn't that cool? Yeah. Of course, there is another way that we use radioactive elements, besides nuclear reactors and besides figuring out how old things are. Can anyone guess what that is? Mm-hmm. Yeah, we figured out a really fun way to use these. Nuclear weapons. All the energy that is released from radiation. You know how damaging radiation is to you? Very much. If you're ever interested in finding out or seeing an example of it, I recommend watching the Chernobyl miniseries on HBO Max. It's brutal. They don't really hold back on showing you the effects of radiation. Radiation is effectively supercharged, super energized particles that are ripping through your body, tearing apart your cells one thing at a time. You actually experience radiation every day when you walk outside under the sun. You have too much of it, you get a sunburn. A sunburn is effectively very minor radiation poisoning. It doesn't really go past your skin. If you're out in the sun for too long, you get what's called sun poisoning. Your skin turns purple and the top few layers die. I've had that several times. It's not fun. Radiation, like from a very acute source, like a bomb or from a reactor accident, literally melts you, tears you apart at the cellular level, reducing you to atoms. I used to live in Japan, and I went and I visited the Hiroshima and Nagasaki Nuclear Holocaust Museum several times. And I saw pictures that they took of people who survived the initial blast, wandered out of the city, and then proceeded to melt in front of other people and die. That's what it does to you. Not fun to see, not fun to experience, I'm sure. The current age we live in, we call it the nuclear age because everyone has nuclear weapons and everyone knows how to make nuclear generators and the such. Nuclear has a lot of potential as an energy source. We'll talk about that when we discuss renewable energy in a future section. Bombs, though, are probably the thing that everyone is most concerned about. Since everyone's got it, it's really hard to control who uses them. The only reason why no one does is because they're afraid that someone else would then use it on them. It's an unfortunate number of unstable monarchs in our world, though, who have these things. Russia has been at the top of the list lately, right? As a matter of fact, Russia has some very fun nuclear history, if you can call it fun. You guys ever heard of the Tsar Bomba? The Tsar Bomba was the largest nuclear weapon ever tested. It was a weapon, a bomb that they blew up on this big banana-shaped island above Russia, right there. Okay? They blew it up right there on the northern part of that island. And this explosion shattered windows across Europe. One bomb that was set off up here shattered windows all across Europe and set off earthquake detectors across the planet. These weapons, as soon as, you can't hide that, right? They tested it, and then the entire world knew that they had it. And so most of the countries in the world got together and said, okay, no one's allowed to use these, okay? And everyone signed it and like, oh, of course, no, never. That would be terrible. You know everyone has them, right? Someone develops it, someone's got it. Probably everyone's got it. The potential for destructive capabilities of these weapons cannot be understated enough. Imagine all the energy that a single isotope is letting off over 307 million years as it decays, and then have a whole bunch of that and release all that energy at once. That's essentially what a nuclear bomb is. 307 million years of energy, all released in a single moment. It literally lights the atmosphere on fire. That's what you see when you see a nuclear weapon blow up. It's lighting the atmosphere on fire. And a bomb that big, you set off enough of them. Conventional nuclear weapons, like what was dropped on Hiroshima and Nagasaki, it would take a couple of dozen of those to reduce every civilized first world country to the Stone Age. It would only take about 8 Tsar Bomba-sized bombs to reduce everyone on the Earth back to the Stone Age. That island up there won't be inhabitable for about 5,000 more years, by the way. So, stuff. Okay. Any questions about isotopes or elements in general? We're about to move on to minerals. That's the next stage. We're moving up. Yeah, you may. Any other questions? Where's the snake at? Right there. Cool. Are you good holding him? All right. Is it interfering with note taking or anything? All right. He will wander around the table, by the way, if you put him down. You just got to watch where he goes because he might get tangled up in your wires, or he might try and go under the table. So just watch that. Okay, let's move on. A mineral. There are many definitions that you will see out there in the world for what a mineral is. The healthcare industry tends to use the word mineral interchangeably with vitamins, right? Drink this shake. It is full of good minerals for you. right? In the mining industry, anything that you can pull out of the ground for monetary value is a mineral. They call it a mineral. They refer to petroleum as a mineral resource, okay? As far as you and I are concerned, geologists, and for every time you're in my classroom for 3 minutes, for 3 hours, twice a week, you are, for all intents and purposes, learning how to be geologists, right? Whether you go on and do that is up to you. What our definition is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. I told you last time that there were only 2 things in this class that I require you to know word for word. That doesn't mean you have to memorize them. It just means that you have to write them down word for word at a minimum. This is the second thing. I gave you the principle of uniformitarianism last time, and now the definition of a mineral. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Why is it important to know this word for word? Because if you take any of those words out, the whole thing changes, right? By the way, it's very easy for me to tell if you did not write this down word for word and then you Google it later. Google will give you a different definition. Okay. You remember the example I gave for the difference between a mineral and a rock last time? I compared a rock to something. What was it? Huh? A cookie. Yes, I said a rock was a cookie, and therefore minerals were what? The ingredients. Thank you. Okay. A mineral has that definition. A rock is a collection of minerals. Okay. A rock is a bunch of minerals that have come together to form a larger substance. In the same way that ingredients of a cookie come together to make a cookie. Y'all got this down? Ready for me to move on? No? Okay. This rock right here, we call this granite. You're probably familiar with granite. I have a chunk of it up here if you want to look at it. Granite is a rock that is made out of the minerals quartz, hornblende amphibole, and feldspar primarily. You good, Karina? Awesome. Okay. Now, minerals have properties. It is through studying, figuring out, learning these properties that we tell them apart from each other. It's very tempting to just say, oh, this one doesn't look like the other one, but that's not always the case. I can have 2 minerals that are totally different colors, but are the same mineral, chemically speaking. Anywhere in this definition of a mineral, do you see color mentioned? No. It has the same chemical formula and crystalline structure. It's the same, regardless of the color. So color can be deceiving. So we don't necessarily put a whole lot of stock in that. It is something that we take note of, but not something we put a lot of stock in. So we have to know what the actual defining characteristic properties of each mineral are. These include things like the optical properties, such as its luster. How does it reflect light? Does it reflect light like a metal, like a glass, like silk, like grease, things like that? What is the shape? These minerals will grow often into geometric shapes. Why? Because a mineral is nothing more than a repeating network of bonds. Those bonds we learned about earlier, it's chemistry. If any of you took chemistry, you probably spent a lot of time working with nice, different colored fluids that you put together and woo, it's like a magic trick. Or you made acids that you really didn't want to touch, right? Or something along the lines. A lot of chemistry focuses on liquids. You know why? Because geology is solid chemistry. Chemistry typically stays with the liquids, maybe even the gases at times. Geology is where we learn about solid chemistry. That's what minerals are. Solid representations of chemical bonds. And because they make geometric chemical bonds, then repeating patterns of that on a larger scale make geometric shapes that reflect it. So shapes like this, representations of the internal atomic bond structure. Okay. you'll see a whole bunch of different shapes as a result of these bonds. The strength of your mineral is another property. Okay, how well does it scratch something? There's not really a scale for this other than just 1 through 10. Okay, we'll learn more about this. It's called the Mohs hardness scale, and I'll tell you what's on there that we can use to compare it to. Density, stuff like density is important. We're not going to go over density in this class. The exercises to learn how to measure a rock's or mineral's density are a little more in depth. So we're not going to worry about that here. If you go on to study geology at the university level, that's definitely something you'll learn there, though. Taste. Taste also can be effective for some minerals. I will tell you right now, though, I'm just going to put this out there right now. At the back of the room are all the practice set minerals for your labs, 1 through 4, labeled, every box. Do not attempt to taste samples 18 or 37. If you do, please tell me immediately so that I can call poison control. Disappointed? Darn. Everything else you can lick. Feel free. Feel free. As a matter of fact, on your lab, there are 2 minerals that look so close to each other, and the easiest way to tell them apart is to lick them.
Wow.
Yeah. Fun. Okay. Oh, for those of you that are doing this online, there are other ways to identify those 2. I gave you some samples in the online lab that you don't have to lick them to tell them apart. It's easier to tell them apart. So don't worry about not being here to lick them. It's not required, just fun. Okay, texture. How does it feel in your hand? Does it feel gritty, slick, smooth? Can you feel any imperfections? Things like that. The smell. Some things have a particular smell, like sulfur. Smells like rotten eggs. Sulfur is a mineral, right? Magnetism. In each of your test kits on the table, I'll get more for this table. For some reason, they're gone. Okay. You'll notice that you have little magnets in each of those test kits. And for those of you watching the video online, you'll see me test each sample with a magnet. Magnetism can be a valuable property to know. And then effervescence. Effervescence is when you drop hydrochloric acid on a substance and it bubbles. It has a reaction. It fizzes. There are 2 minerals in your lab that you are going to see that effervesce. One does so very easily. You just put some acid on there and it instantly fizzes. You can even hear it. The other one, you're not really going to know what it is. It's going to be difficult to tell, but if you scratch a little bit off, scratch a little dust off, maybe with a piece of glass or a penny or something, and then you put some acid on it, it will gently fizz. That's your indicator for what you're looking at there. Okay? Remember that if you're ever stuck on one, just be like, huh, he said there was one that would gently fizz if I dusted some of it off. Let's see if it's this one. Okay? Why does this happen? Well, what you have here is hydrochloric acid. Each test kit has a small vial of hydrochloric acid. Safety point, that is not water. It is acid. It's not enough to hurt you, though. Okay, I dilute it. If you get some on your skin's going to feel like a little slick. It's just dissolving the outer layer of skin. It's not going to hurt you. That layer of skin is dead already anyway. You won't feel anything. But please, 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 be careful not to get it on your clothes. It 100% will dissolve those. Matter of fact, I don't have any on this shirt. This is a relatively new shirt. Most of my shirts have holes all over them because I accidentally get a drop of hydrochloric acid on my clothes all the time. It's my wife's least favorite thing. She's like, we go through so many shirts for you. It's like, yeah, I go through a lot of acid. Don't cut that. I just don't, no one do anything with that clip, please. Yeah, don't clip me. Please don't clip me. Okay, but this is hydrochloric acid. Okay, so just be careful with it. It won't react with anything other than those 2 minerals in this way anyways. Okay. Okay, so let's talk about each of these properties in a little bit more detail. For optical properties, we've got the luster, how light interacts off the surface, how it reflects off the surface. You would use words to describe these like metallic, submetallic, if it looks like it's metal, but a little bit duller. It's not super glossy. Glassy or vitreous is a word that you use to describe glassy as well. Okay. Does it look like mother of pearl? Does it look like resin from like dried tree sap? These are words that we use to describe them. You don't necessarily have to stick to the words I've given you here. You can use your own descriptive word. It just has to make sense. You know? Right? These are your observations, by the way. I'm giving you ideas for how to fill out the requirements for lab. It's your observations, though. So if it makes sense to you, make sure that as you write it, the way that you're describing it should make sense to me as well. All right, another optical property is how translucent it is. Opaque means no light can go through it. Translucent means light but no image can go through it. And transparent means light and an image can go through it, like clear glass. Easy way to tell this on your lab, turn the flashlight on your phone, put your phone screen down on the table, and then put your sample on top of the flashlight. You'll be able to tell immediately if it's opaque, transparent, or translucent. Okay? And then finally, color. Color, we don't put a lot of stock in, like I said earlier, but it can be a good tiebreaker. We usually only use color as a good tiebreaker if it ever comes up. So it's worth noting. The last optical property that you'll observe is called streak. For this, in each of your test kits, I give you a piece of unglazed white porcelain. There's also unglazed black porcelain in there. If you have a light colored mineral and you scratch it on a white streak plate, you probably won't be able to see it very well, so I give you a black one, right? And vice versa, if you scratch a black mineral on a black streak plate, you might not be able to tell. Why do we do this? Well, because when you scratch a mineral on something harder than that mineral, it leaves behind some residue, and that residue may be a totally different color than what the color of the mineral appears to be. This is valuable because what you are actually seeing may be the true color of the mineral, whereas what the mineral looks like could simply be the oxidized outer layer. Interaction with the atmosphere can change colors. Think rust, right? So this is called streak. Now, if your mineral leaves no streak but leaves a scratch, what does that tell you about your mineral? Oh, there we go. A couple of you got it. It's harder than your streak plate. So in that case, it's totally appropriate to say no data for the streak. It is appropriate to say no data for any of these if you simply can't tell. But be very cautious with how you use that, because if you do it too much, you won't have enough data to figure out what your sample is. Okay? I don't expect you to make anything up. I expect you to use science and experimentation to figure out what the data is. But if it's impossible to get data off of it, I can't expect you to give it to me, can I? This is the real world. Okay. Crystal shapes, some examples. There are dozens of different shapes, but here's some fun examples. Magnetite octahedrons. It will actually make these kind of double pyramid-sided shapes. That's how it naturally grows. By the way, magnetite. Can you imagine one property magnetite has? Yeah, it's magnetic. Yes. It will attract the magnet. Garnets. If you've ever seen the gemstone garnet, this is the shape that they naturally grow into. I have several up here if you wanted to look at them later, okay? Dodecahedrons, 12-sided shapes. They naturally grow into that. Halite grows into cubes. Anyone want to guess what halite is? Huh? No. This is salt. Halite is the geological name, the mineral name of salt. Salt naturally forms this cubic shape. Hexahedron, we call that, or a cube. That's just a few examples of shapes. There's a whole website that I give you access to that has all the possible crystal shapes on there, and you'll be using that in the lab. Tenacity is the manner in which a mineral will break. Will it bend? Is it malleable like Play-Doh? Can you shape it? Will it snap? Will it shatter like glass? These are different types of tenacities, right? Now, I don't expect you, nor do I want you, to attempt to break my samples. Please don't. I can't. I'm not a big department. I'm a department of one dude. I can't afford to replace my samples every semester. So please don't break them. Instead, when you are observing the tenacity, most of your samples are already broken in some way. You will simply be using your best educated guess to see, okay, this looks like it's part of something that shattered. Or, huh, this one bends a little. You know, don't actually break it. You know, give it your best guess as far as tenacity goes without actually giving you hammers and saying, go nuts. That's the best we can do. Hardness. In the same way that I can't afford to let you break my samples, I also can't afford to get all of you full hardness test kits that go 1 through 9. Okay? Like I said earlier, we have the Mohs hardness scale. The Mohs hardness scale goes 1 through 10. Talc, gypsum, calcite, fluorite, apatite, orthoclase, feldspar, quartz, topaz, corundum, and number 10, diamond. So you can tell why we don't have number 10 scale here, right? Can't really get a diamond tip on a pen. Okay. I do not give you these test kits, but I do give you glass. Glass has a hardness of 5.5. Each of you has a sheet of glass in your test kit. Next safety point, when you are testing the hardness of a mineral, please put the glass flat on your table before scratching your mineral on it. You're going to want to put a little bit of elbow into that so you can actually see if it will scratch the glass. Instead of putting the glass on your hand with the potential to break, right? Put it flat on the table. No injuries in our class, okay? Same thing with the streak plates. Flat on the table and then scratch. If your mineral scratches the glass, what does that tell you about it? It's harder than when glass is 5.5. Your mineral is harder than 5.5 if it scratches. So in that case on the lab, you would just put greater than 5.5. If it does not scratch the glass, it's softer than 5.5, and you would put less than 5.5. Okay? You don't need to give me a specific number. I can't expect you to give me a specific number because I'm only giving you 1 point of reference, aka the glass. Greater than 5.5, less than 5.5, that's it for hardness. Cool? All right, cleavage. Cleavage is probably the most difficult part for students to pick up about minerals. Cleavage is the manner in which a mineral breaks based upon its internal atomic structure. Let me explain that. I said earlier that a mineral is a repeating pattern of the same atomic bonds that are at the molecular level, right? The microscopic atomic level within that mineral. They just keep repeating on top of each other, building the structure out, which means that if I have a bond that is weaker than the other bonds, and then I put pressure on those bonds, which one's going to break first? The weakest one will break first, right? And since this is a repeating pattern through the whole structure of the mineral, guess what? That bond will break along the same direction throughout the entire structure of my mineral. And just like that, I get a separation of my mineral. It is broken along this one plane of weakness. That is called a cleavage plane. When you are going to tell me what cleavage the mineral has, you're going to tell me how many planes, which are usually flat, quite flat, okay? How many broken flat surfaces there are, basically. Different planes, though, is the key. To help understand this principle, I have actually 3D printed, I actually designed these. I have a patent on these because no one else had done this yet, I guess, which was crazy to me. Okay? I made these 3D models to help you understand cleavage a little bit better. Okay? I'm going to stand right here so that the people watching this online can see it better. All right? When a mineral has one plane of cleavage, that means that there is one weakness surface within it, and it will break in repeatedly along that same surface, like this. Okay? It'll break off in effectively sheets, one layer at a time. That is one plane of cleavage. Okay? When a mineral has two planes of cleavage, then it gets a little more complicated because now all of a sudden we're not just talking about different planes, we're talking about the angles between those planes. Now, I don't expect you to whip out a protractor on all of these and tell me what the angles are. However, you do need to tell me if those angles seem to be at 90 degrees or not at 90 degrees. That's as specific as you need to get. For a mineral that has two planes of cleavage at 90 degrees, you'll get something that looks like this when it's broken, where you have, there's one plane, and there's another plane at about 90 degrees. Now, what's the obvious problem here? Someone pointed out. I told you that this has 2 planes of cleavage, but how many sides are there?
4.
4. What's the difference, though? I said planes, not sides. This plane and this plane are the same plane, just on different sides of the mineral. They are breaking in the same direction, making them the same plane of cleavage, simply on 2 different sides of the mineral. Same thing with this plane and that plane. So even though there are 4 flat broken surfaces here, because 2 of them are parallel to the other 2, there's only 2 planes of cleavage. Make sense? You know what doesn't make sense? A penny. It makes 1 cent. I got you again. Okay. All right. So that's 2 planes of cleavage. That's 2 planes of cleavage at about 90 degrees. 2 planes of cleavage not at 90 degrees is going to look like this. Cleavage plane, same cleavage plane. Cleavage plane, same cleavage plane. 2 sides, but not 90 degrees. Not 90 degrees. Okay? 3 planes of cleavage at 90 degrees. Breaks here, breaks here, breaks here. All the angles are 90 degrees. Makes a box shape. Okay, a cube shape. And if a chunk of this were to fall out, it would be a smaller cube shape. Okay? 3 planes at 90 degrees. 3 planes not at 90 degrees. Looks like this. Plane, plane, plane. Not 90, not 90, not 90. Kind of a rhombohedron sort of shape. And when you break it into smaller pieces, they make smaller rhombohedrons because they break along the same cleavage planes. And then the most complicated one I'm going to give you, I'm just going to let you know right now, cleavage in nature does go up to like 12 planes of cleavage. I'm not that mean, okay? Most I'm going to give you is 4 planes of cleavage, okay? In 4 planes of cleavage, you make this sort of shape. Cleavage plane, cleavage plane, cleavage plane, cleavage plane. The opposite of this one is over here. Those are the same plane. The opposite of this one is right here. Same plane. So it breaks off here, 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 and here, 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 here. But 4 of these are parallel to the other 4. So you have 4 planes of cleavage. Okay? Are your eyes cross-eyed yet? Some of you. You'll be fine. You can ask me for help. Okay, that is cleavage. Questions about cleavage? Yes?
Why was the concept made up for it?
Why do we care?
Like, why do we use that system?
Because it is a characteristic unique to many different forms of minerals, which means that it's important to take note of for those of us that worry about classifying such things. There are lots of different types of minerals. We'll talk about that here in a minute, and therefore we needed a way to tell them apart. So cleavage is one way to do that. Any other questions? Yeah.
Do some minerals have no cleavage?
Absolutely. That's the next thing, actually. When a mineral has no cleavage, it has fracture. So why would a mineral have no cleavage? If cleavage is a plane of weakness, then a mineral with no cleavage would therefore have no uniquely weak planes, right? No uniquely weak bonds. This is common in substances that have the same bond throughout the entire thing. If I have a substance that has hydrogens bonded to carbons, bonded to silicons, bonded to X, bonded to Y, bonded to Z, there's a lot of different possibilities for what could be weaker and what could be stronger. But if I just have silicon bonded to oxygen and that's it, all my bonds are going to be equally strong in every direction, right? So in the case of that example I just gave, silicon dioxide, right? That's quartz. Quartz does not have cleavage. It has what we call conchoidal fracture. It kind of, when you break it, it makes a sort of scooped out, ripply sort of look. That's what conchoidal fracture looks like. Some glass does the same thing, by the way. If you've ever seen glass, like a big piece of glass, and it's like broken, and it's got that sort of ripply surface on it, that's conchoidal fracture. Density, we're not really worried about in this class. By the way, if you get this meme, props to you. Your parents raised you well, or you're as old as me. Anyone get this? You get this? Back to the Future? Yeah? Yeah. What's that face, Alyssa? What? All right. This is now turned from a geology course to an appreciation of classic film course. Okay? All right. There's taste, there's texture, smell, magnetism. I talked about all this. Effervescence. I already gave you the safety points on all these things. Glass and streak plates flat on the surface of your desk before you use them. Acid, make sure you don't get it on your clothes. If you do use acid on something, please wipe off the residue with paper towels from the dispenser at the back of the room. You don't need to wash off the samples. The acid that's left behind will evaporate off of the surface within 30 minutes. Don't taste a mineral that someone has already put acid on. It won't hurt you. Your tongue may feel a little fuzzy, or like maybe not really numb, but like, you know that feeling like if you've scraped your tongue with your teeth and it's like, feels like there's something on my tongue, you know? It would feel like that for a while. That's pretty much it. But don't do it. Okay. Those are the properties. Shall we talk about minerals specifically? Let's do it. There are over 4,000 different minerals that we have identified on our planet. We have 8 weeks. Are you ready for this? No? Well, that's a good thing because I'm not actually going to make you do that. I give you 51 practice set minerals, but you only have to identify 24 on the lab. Okay? Sound a little more achievable? Good. Keep that optimism. All right. So we break minerals down into 2 basic categories right off the bat: silicates and non-silicates. All the silicate minerals are based around the same initial structure. The non-silicates are not. Okay? Silicates make a large portion, about 90-something, 91, 92% of our surface, okay, are silicate minerals. Silicates are formed through igneous processes, which we will learn more about next week. Okay, silicates, though, are built around this first initial structure. This is the first part of a silicate mineral that forms. It's called a silicon tetrahedron. This is a covalent bond between one silicon, which has a +4 charge, okay, and 4 oxygens, each of which have -2 charge, which means that it is constantly rotating between 2 of these oxygens at a time for sharing that charge. This entire thing has a net -4 charge, which means that it is great for bonding with metals. The combination of metals plus the silicon tetrahedron make many of the minerals we have on our planet. Now, silicon tetrahedrons can bond with each other. When they do, so we go from independent tetrahedrons, we will start to form things like single chain tetrahedrons, double chain tetrahedrons, sheet structures, and 3-dimensional frameworks of tetrahedrons. This tends to happen as magma is cooling off. As magma starts to cool, you form your tetrahedrons. Then as it cools more, you get your single chains, and then it cools more, you get your doubles, and then your sheets, and then 3-dimensional frameworks. 3-dimensional framework minerals tend to be more tightly bound, tend to be stronger in general than the other types. Okay. Because of the nature of this, and because silicons end up sharing oxygens between each other, you actually eliminate the number of oxygens required in these, so that by the time you get down here, instead of having a 4-to-1 ratio of oxygens to silicons, you have a 3-to-1 ratio, and then finally a 2-to-1 ratio in this tightly bound 3-dimensional framework. An example would be olivine, the mineral olivine. We'll talk about more of that in a second. But this is the chemical recipe, so to speak, for olivine, the mineral olivine. Look at what's on the end here. What is that? I mean, yes, you're right. That's a 4 subscript. I'm talking about this whole thing. That's a silicon tetrahedron. 1 silicon, 4 oxygens. That's our silicon tetrahedron right here at the end. Okay. What else does it have? 2 irons and magnesiums. and a single magnesium. Although for the mineral olivine, those are interchangeable. Why are they interchangeable? Well, look at magnesium and iron. Both of them have a +2 charge, and they are about the same size shape of an atom. Same size, which means that they can swap interchangeably for each other in certain things. Olivine, the mineral olivine, you can swap out the ratio of irons to magnesiums, and it really won't make a difference to the structure of the mineral. And so even though that sort of chemical swapping happens, we still refer to that structure as an olivine, even though there's a slight variation in the chemical recipe. Okay. The same thing can happen with aluminum and silicon in some places. We'll find that some aluminum, some silicon tetrahedrons, the silicon has been swapped for an aluminum. That'll happen sometimes. So irons and magnesiums can swap, aluminums and silicons can swap. It just kind of depends on the heat, the pressure, and what's available. Okay, let's talk about some of the more common silicate minerals that we see on our planet. We separate silicate minerals into light silicates and dark silicates. Can you imagine why we do that? Because some of them are, some of them are lighter colored and some of them are darker colored. Exactly. That's the only reason. Why would you have some that are lighter and some that are darker? What could influence the color of these minerals?
Pressure?
Not the pressure.
The heat?
Not the heat. The elements. Yeah, bingo. What is color even? It is reflected light based off the wavelengths we can perceive. I'm going to go on a tangent here. Are you ready for a fun tangent? You ready for a cool tangent? Let's talk about other planets for a second. Okay, and let's talk about plants and planets. Here on Earth, most plants are what color?
Green.
Green. Why? What? Chlorophyll isn't green. Chlorophyll is a chemical that does a certain function. Also, it is a cell that does a certain function. Why the color green? Pigment? Not really. I mean, the pigment for green in plants is what we observe, but why green?
Because that's the color that gets reflected into our brain.
There it is. Green is the only color of light that comes from the sun that plants do not absorb. It's what they reflect off. Therefore, green is what we observe plants to be. Every other wavelength is absorbed. What if there are plants on other planets that are red? Plants on other planets that are purple? Plants on other planets that are black? What would that mean? What would a black plant mean? What wavelengths does it reflect?
Black.
All of them.
None of them.
None of them.
A black plant would absorb every wavelength and not reflect anything. Yeah. Light is reflected off of surfaces, and the reflected light that we observe into our ocular devices called eyes, that's the color we perceive, which is why some people have slight variations in the colors that they observe things. Was the dress blue or was it gold? I don't know. I saw something, you saw something else. You guys remember that thing? Right. They do stuff like that all the time, playing with this fact that there is slight variation in our eyes and in the wavelengths that we absorb. Well, the same thing is true for minerals, okay? Light silicates, dark silicates, it's the light that is reflected off of the surface or out of the interior crystalline structure, okay? So, our dark silicates, starting up here, olivine, pyroxene, it says augite, that's a variation of pyroxene. Hornblende, which is a type of something called an amphibole, which you will learn, okay? Biotite, muscovite, feldspar, quartz. Now, in addition to this, notice how we're going from independent tetrahedra down to single chain structures, double chain structures, sheet structures, and three-dimensional frameworks. Remember what I said that was tied to in the magma? What's happening here at the same time? As we go through this, what's going down? Huh?
The magma is cooling?
It's cooling off. Heat is dropping. Wow, that was an E and an A somehow at the same time. Okay. Heat is dropping at the same time we're going through that progression. That's going to be vastly important next week when we learn about magmas. and the volcanic processes. Excuse me. I got too enthusiastic there for a second. Okay, so we're going to talk about these. We're going to start off with the light silicates, though, and then we'll talk about the dark silicates. Some of the more common light silicates. Oh, wait, before I move on to that, I never explained why they are different colors, why some wavelengths are reflected. We call another name for our light silicates is non-ferromagnesian, and dark silicates is ferromagnesian. Anyone want to guess what that means? What does? Which ones? They're all silicates. Which ones have iron? Ferromagnesian minerals have iron. That's the ferro. And magnesium. You remember those 8 most common elements that we have on the surface of our planet? Iron and magnesium are 2 of those. The silicates that possess high quantities of iron and magnesium not only are denser, but also darker colored because they have iron and magnesium in them. Whereas the non-ferromagnesians have how many? None. They are non-ferromagnesian, right? They are lighter colored, okay? So the non-ferromagnesians are light silicates. Feldspar. Feldspar, there are many varieties of feldspar. You'll learn about 2 in our class. They make up about 50% of the crust. And there's a fair amount of it in the mantle too, but about 50% of our crust is made out of one variation or another of feldspar. Give you some of the properties for them here. 2 planes of cleavage at or near 90 degrees. Let me give you an example, just to help you understand cleavage a little better. This is an unbroken crystal of feldspar, making this unique geometric shape with all these sides. Nice, beautiful, unbroken. One of my favorite samples because it's actually pretty difficult to find nice unbroken euhedral minerals, we call that. Okay. Now, if I were to break this, if I were to smash this with a hammer, which I will not do because I love it, I would get a manifestation of its cleavage planes. Yeah, don't go nuts. Don't go crazy, Marquez, on my stuff. No hammers for you. Okay. I would get something that looks like this. Very different shape. 2 planes, 1, 2, at about 90 degrees. Okay. 2 planes at about 90 degrees. This is feldspar that has been broken so that we can see its cleavage. Very different from this, right? I'm going to pass these around so that you can see them in better detail. Okay, so the 2 types of feldspars that you're going to learn in this class, potassium feldspars and plagioclase feldspars. There are many different variations in color between these. Some colors are shared between the 2 types, though, which is why it's not a primary identifier. However, the best way to tell the difference between potassium and plagioclase feldspar is that plagioclase has what are called striations on the cleavage plane. If you look closely at this image, and on the screen here it may be difficult to see, but if you look on your laptop and zoom in a little bit on the PowerPoint slide, you will see parallel grooves in this surface running in the direction these arrows are indicating. And in a real life physical sample, if you were to shine it in the light, you would see the same thing. For those of you watching this online, for the lab, I did videos of 360-degree rotating views of all of these samples with light shining on them. And in the right angle, you will see these striation planes on the cleavage planes of plagioclase feldspar. Okay, that's feldspar. Next up, we've got quartz. Everyone's favorite, right? There are many varieties of quartz. How many of you like amethyst? Amethyst is not its own unique mineral. I have a bunch of amethyst up here, actually. Amethyst is just quartz. Do you know that? It's not its own mineral. It is quartz. It is quartz with a little bit of something in it, giving it that purple color. Iron in this case. Okay? Iron gives it that purple color because it's reflecting that wavelength out of the structure. Then we've got rose quartz. Rose quartz has a little potassium in it. Okay. Then we've got smoky quartz. Smoky quartz has a little uranium in it. Then you've got milky quartz that has a little calcium or sodium in it. Okay. We call these inclusions. When you get something in the atomic structure of a mineral that is not actually incorporated into the chemistry, like the actual atomic structure, it's not influencing the bonds or anything, but it's stuck in there between the bonds, let's say, that's called an inclusion, and that can change the color of your mineral. All these different varieties of quartz, no matter what else is in them, are still quartz, SiO2. Okay? And then we would say, in the case of amethyst, SiO2 parentheses Fe, to show that there's some irons in there as well, giving it that color, right? Muscovite. Muscovite has one plane of cleavage. It breaks off in sheets. What you're seeing is this is a crystal of muscovite. That's a crystal, that's a crystal, that's a crystal. But they're very thin sheets that break off of each other. That is one plane of cleavage. Very soft mineral. Ladies, if any of you have makeup that has glitter in it, that's usually crushed muscovite. Yeah. Interesting fun fact. Yeah.
Is it similar to like
Mica powder? Yeah, muscovite is mica. It is a form of mica, as is biotite, which we will learn about when we go to the dark silicates. That is exactly mica powder. Clay. Now, clay is what we call a secondary mineral. Clay is the result of the breakdown of these silicates. We'll learn more about that when we discuss sediments and weathering and erosion here in a few weeks. But clays have a very long, complicated chemical structure, which I won't go into, but there's a lot of aluminums in them, which makes them very valuable for mining aluminum and such. Clays make the foundation of a lot of the dirt and soils that we use. But also, how many of you like milkshakes? I hope you still like milkshakes after this. You ever wondered how they get milkshakes to that consistency where it's really cold, but like it's not frozen, but somehow it's still thick? They use clay. Clay has excellent water absorbing properties and is not harmful to you, but they use small quantities of clay when they mix up the milkshakes to give it that thick consistency. I won't say you're drinking mud, but it's like delicious mud. Very, very small amount of it. Yeah. All right. See, your world revolves around geology more than you thought it did, doesn't it? I'm not saying your world revolves around milkshakes. I wish mine did. All right. Now let's talk about the dark silicates. Let's start off with olivine. I showed you this sample last time we met. This rock is peridotite. Most of the mantle is made of peridotite, right? However, the minerals in peridotite, there are two of them. This green one, olivine. I bet you can't guess why it's called olivine. Because it's green, right? In case you aren't aware, classic olives are green. Black olives are man-made creations. Okay, normal, natural olives throughout most of history have been green. I actually like green olives. How many of you like green olives? I like their flavor. They're great on pizza. You're giving me that look again, Alyssa. I hope we can stay friends after this. You don't know? Jury's out on that? All right. Well, this green mineral is olivine. The black ones that you see in there, those are pyroxenes, which we'll talk about on the next slide. Okay? Olivines are made of those independent tetrahedral structures. They're actually quite hard. However, most of the mantle is made out of olivine. Let me ask you this question. What do you suppose happens when you bring olivine to the surface? No, it's always green. Actually, that's a good philosophical question. I don't know if you meant for this to go there. Is it green if we're not looking at it? If a tree falls in the woods and no one's there to hear it, does it make a sound?
Yes,
He says yes. How do you know?
because it vibrates the air.
Yeah, but we're not there to observe it.
The air is still vibrating regardless of whether or not we're there.
But does a vibration make a sound, or is it only a sound once our ears absorb the vibration?
We can ask the animals that way.
Right, exactly. So Here's one of those tangents, right? Is it green even though we're not looking at it? I don't know. I'm sure that's not where you meant for that question to go, but that's where I took it. Ha. Okay. What was my question? What happens to olivine when it reaches the surface? Think about how deep the mantle is. We're talking about kilometers deep. At the very least, under the oceanic plate, at least 7 or 8 kilometers deep. You bring it up to the surface. What's different up here? It's colder. There's less pressure. This mineral that formed under high temperatures and pressures, do you think it's going to respond well up here? No, because in general, all things in nature are seeking, was the word I used earlier, stability. It's going to break down. It's going to weather. It's going to erode. It's going to do all that stuff. It's going to break down, right? So olivines form at deep temperatures under deep pressures. They don't respond or last long up here, typically, okay? Then we've got pyroxene. Pyroxenes form at slightly lower temperatures than olivines. They are single chain structures. They are black in coloration. They have 2 planes of cleavage at about 90 degrees, which is important because the next one we're talking about, amphibole, looks almost exactly the same as pyroxene. It's that black color, which is why you cannot always use color to identify, right? But the cleavage is 2 planes not at 90 degrees. So if both of these appear on your labs, they will, then the best way to tell them apart from each other is look for those cleavage planes. Am I looking at a black mineral that has all these properties? It could be either pyroxene or amphibole, but are the cleavage planes at 90 or not at 90? That's how you'll tell them apart. Okay? Then we've got biotite, the other kind of mica that we learned about. You actually have 4 types of mica that are practice set minerals there along the back. Lepidolite, phlogpite are the other 2. But biotite is the fully ferromagnesian darker version. Okay, it's a little bit harder, but not by much than muscovite. Has that same pearly luster, but it's dark colored because it has irons and magnesiums in its structure, whereas muscovite does not. Garnet. Garnet is a gemstone, but it's not only a gemstone. It's actually pretty hard and relatively easy to manufacture. We use them as industrial abrasives a lot, actually. Okay. I refer to garnet as the trash can rock, not because it's not pretty or cool or anything like that. Garnets tend to form in igneous and metamorphic rocks out of the leftovers. Okay, there are several different varieties of garnet, and they kind of just form after everything else forms out of whatever's left over. It'll kind of just make garnets, but they're still really pretty. And then now let's talk about non-silicates. Non-silicate minerals are the vast minority of minerals on our planet. Okay, they include all of these. We break non-silicates because they are not all bound by that same silicon tetrahedron structure. We bind them together. We classify them based upon the ion that they have in common. Okay, so for example, our carbonates are bound by the CO3 2 negative, right? Our oxides are bound by this O2 negative. What are some common oxides? Can anyone read these for me? No? A little bit difficult. We've got hematite, magnetite, corundum, which you may know of as ruby. Okay. And then what's this?
Ice.
Why is ice on here? That must be a typo. This is a list of minerals.
It's solid and crystalline.
What's the definition of a mineral? Give it to me. Whoever gets there first, go for it.
Any naturally occurring.
Loud.
Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula.
Does ice match that?
Yeah.
Any naturally occurring, check. Inorganic, check. Solid, check. Possesses an orderly crystalline structure, check. And has a chemical formula. What's the chemical formula? H2O! Ice is a mineral, guys. Yeah, that's why we have a whole lecture on glaciers in Module 2. Glaciers, believe it or not, glacial studies, that's grouped into geology. Because ice is a mineral. Okay, it's cool. All right, so ice is a mineral. All of those are minerals. These are actually extremely valuable mining resources. Why? Because we've got a whole bunch of our valuable metals down here. We've got a whole bunch of stuff that we can extract valuable properties from, like sulfates. We get a whole bunch out of those, right? A whole bunch of these are mining targets for the reason that they encompass a whole bunch of the elements that are relatively rare in the silicates. Now let's talk about mining for a second here. Okay, we're almost done. I just hit my hour and 30-minute mark, which means that we're just a couple minutes away from lab time. Let's talk about mineral resources here for a minute. Our civilization would not exist without mining resources. You guys believe me? It is very tempting to jump on board with the people who say things like, we need to stop mining our planet. We need to stop producing oil. And maybe it's not so tempting to jump on board with that here where we live, because a lot of y'all's families, a lot of our economy here relies upon the oil industry. But there's a lot of people who make compelling arguments, and there's a lot of really loud, obnoxious people who say things like that, right? And I'm not going to say they're wrong. It is indisputable the sort of effect that mining and oil production has done to our planet. You cannot fight that, especially if you know the science like I do. I'll talk more about that later on. But it is also indisputable that we would not be where we are as a civilization without those resources. And we will not proceed any further as a civilization unless we continue to use those resources. So the trick is figuring out how to find that careful balance between the two things. Okay? How do we get the resources we need without completely annihilating the things on our planet to make our planet a nice place to live? That's the trick. Now, the things that you take for granted in your life, your phones, your laptops, your glasses, plastic. You guys know where plastic comes from? Yeah. When you get petroleum out of the ground, it looks like this. Thick, gooey tar. That doesn't look like the gasoline you put in your car, does it? How does it get there? We have to refine it. Where does all that stuff that makes this black, gooey tar go? Make plastic out of it. Can you imagine your world without plastic right now? If we were to just cut off the petroleum industry, if we were to say all 100% renewable today, which by the way is impossible, but we'll talk about that later, okay? If you were to just do that today, if magically we were able to give everyone rechargeable batteries to fulfill every need and no one had to use gasoline or any sort of fossil fuel ever again, all of a sudden plastic would disappear too. What did we use in the place of plastic before we had plastic? Some of it was metal. Most of it was wood. Are you ready to start chopping down all the forests again to replace the plastic that we no longer generate? No. None of these are easy questions. Part of what I hope you get out of this class is a little bit better context and a little bit of better information for you to be able to think about these questions for yourself. I'm not going to say I'm going to give you answers. Some of the things I tell you are good enough answers for me. They may not be for you, but what I hope you get out of this class is the ability to think for yourself while you investigate these things. Okay? Now, mining. If you've ever heard the term ore before, ore is rock that is bearing a certain resource that you want to target. Okay? Some resource. Let's say that we've got gold. I used to work at a gold mine in Nevada. Okay, my job was to go around and explore out in the middle of nowhere and find places that had the ore that had enough gold in it, the rock that had enough gold in it that we could call it ore and mine there. Okay. If a rock does not have enough of a certain resource in it, we simply don't target it. What is enough of a resource? Enough to make a profit on. No company anywhere is going to ever mine anything without the ability to make a profit on it. That's how businesses work, okay? So at my gold mine that I worked at, our cutoff was 0.03 parts per million. If rock had 0.03 parts per million or more in it, we parked a mine on top of it. We mined that out. That's not a lot of gold. But when you consider the fact that each truck, have you ever seen a mining truck, by the way, a haul truck? The tires are 2 stories tall. The truck, to get to the cab, you have to go up 3 flights of steps. Each truck holds 500 tons of rock. So yeah, and here's me in my little exploration pickup, like doo 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 doo, and here's these mountains of trucks passing me. It was really fun, dangerous, but it was really fun. But when you're talking about each truckload being 500 tons of rock, are you looking at the pictures? Yeah, they're huge, aren't they? Then 0.03 parts per million all of a sudden becomes sustainable, becomes doable, especially when you consider gold is like $3,000 an ounce at the time, right? You generate 1 ounce of gold out of a couple of truckloads. That's $3,000 that you just generated from a couple of truckloads. You make a good profit off of that. It's sustainable. Obviously, we'd look for better than that, but that was our bare minimum of what we could generate, okay? Every mine has to face the same thing. This is a copper mine, the Bingham Canyon Copper Mine. Decades back, about 40 years ago, I believe it was, China opened a new copper mine that all of a sudden started putting out businesses, copper mine businesses in other parts of the world. China will do this every now and then, okay? In case you're not aware on the geopolitical situation with China, they have everyone by the family jewels in a lot of ways, okay? One of the ways is through mineral resources. When it came to copper, they opened a brand new copper mine and then sold the copper dirt cheap. Who's gonna buy copper from the Bingham Canyon Copper Mine in the United States if you can buy it for half the price from China? No one. And so they started forcing other copper mines out of business. So Bingham Canyon had an opportunity. They had a choice to make here. Do we sell off everything right now and save whatever we can and just get away with whatever money we can get away with? Or do we spend a whole bunch of money, about $100 million, to revamp our whole facility to make our production more competitive and more efficient? They chose to revamp the facility. And they spent that $100 million. They made the process way more efficient, which meant that they could drop the price and compete with China. And now it is still an operating copper mine that we have here, one of the largest, actually. In case you're wondering, yes, those are mountains, and this is the mine. You can fit a couple of those in this mine, okay? It's right up against those mountains. Huge mine, huge operation, and because they made that choice, the United States is not 100% dependent on China for copper. It has maintained a lot of our independence in that regard. China has done that in a whole bunch of mineral markets, though. There are what we call rare earth elements here on the bottom of our periodic table of elements there, okay? Many of those rare earth elements are required for advanced technology. Your smartphones, your laptops, night vision goggles, Tomahawk missiles for the military, Xboxes, Wiis, PlayStations, all of those require at least one or more rare earth elements in some quantity, either as a conductor or to help in processing capabilities. China has 98% of the world market on rare earth elements, all 17 of them. So they get to dictate who gets it. And anytime someone threatens to piss them off, all they have to do is say, all right, do what you want. We may not send any of these metals your way, though. And all it would take, 10, 20 years when all the reserves are gone, no one has any more of those. We piss off China enough, 20 years in the future, we have no technology that can compete with anyone because we can't make it. And every time someone tries to open another rare earth metal mine, they drop the price on rare earth metals and make it unsustainable to open a new mine. There's a place in California that they've tried reopening, I believe, 3 times now. It takes about $5 billion to get operations going there because these things are so rare. But every time that someone tries to reopen it, China drops the price and makes the project untenable. And that's how they keep everyone under the thumb. They don't own everyone militarily, but they sure as heck own us all mineralogically in this regard anyway. Yeah, world politics relies a lot on things like this, and you don't know about it until you come in my class. Okay, that's all I've got for you today for lecture. Any questions about what we've learned? Nothing? Y'all understood everything? Some hyper intelligent people here. I love it. Okay, well, in that case, let's move on to lab time. There is a Lab 1 PowerPoint. Let me close this real quick. There is a Lab 1 PowerPoint that you have on Blackboard. Let me navigate to it myself here. There it is. Most of that PowerPoint is review of what we just discussed in class, but there are a few important things that you need to know about as a resource to help with the lab. What? Yes, you may. Okay, when you go Oh, okay, so I got to show this all to you. Let me make sure my sound is on. Yeah, it's all the way up. All right, cool. Y'all ever seen Journey to the Center of the Earth with Brendan Fraser? It's a fun movie, totally ridiculous. It is on the list of ridiculous movies to watch. But there's a part of it that I absolutely love. So Brendan Fraser and his nephew and their guide walk into a volcanic tube. Okay, that's setting you up for this. Listen to what they're saying when they walk into that tube. Hold on, it's not. Let me change the speakers. It's not piping through the projector. Hello? Why you no go to projector? Oh, here we go. Okay, here we go.
Rubies. Emeralds.
Feldspar.
He's the geologist, can you tell? Everyone else was like, look at all these jewels. And he was like, oh, there's feldspar. Feldspar making 50% of the planet's crust, right? That's why it's funny to geologists. I don't know. Maybe, yeah. Okay, so we learned about all those properties, right? You're going to be identifying them in the lab today. Here are some examples of crystal forms, aka shapes. Here are some other examples of shapes. But the most important thing here for you to note is this website. You will want to go to that website. It is hosted in the Netherlands. See that smorf.nl? That means Netherlands. Okay. .com is usually websites that are hosted in the United States or a United States-owned property. Okay. .nl means it's hosted in the Netherlands. So you may have some trouble navigating to it on the Odessa College Wi-Fi. Some people do, some people don't. If you're using an ECISD laptop, that may also give you a hard time. But this website has a database of all of the possible crystal shapes. And they're all like rotating. So like all you have to do is count the number of unbroken sides on your mineral, if it has unbroken sides. And then go to that website and say, this mineral on my lab has 6 unbroken sides. I'm going to look at all the 6-sided shapes on this website and find the one that matches it. And boom, just like that, you've got the first part done. You found your crystal shape. Okay? Easy. Now, where that becomes uneasy is if your mineral is too broken. If your mineral is too broken and you don't have enough sides to tell what its original shape was, what do you put? Say it louder. Na. No data. Either one of those works. Again, I don't expect you to make up work. However, here's the kicker. If you have a broken mineral and you cannot tell what its crystal shape was, then what do you definitely have enough data for? The cleavage. The cleavage requires broken surfaces. Crystal shape is unbroken surfaces. You will either be able to tell me what the crystal shape is or what the cleavage is, and for a few of them, you may even be able to tell me both, but you absolutely, on every sample, should be able to tell me one of them. And just say no data for the other one. If it's too broken, no data for crystal shape. If it's totally not broken at all, plenty of crystal shape data, no cleavage data. Make sense? Either way, you have valuable information to help you identify what you're looking at. Okay, so there's cleavage. You're going to have either 1, 2, 3, or 4. Forget that I said 6 sides there. You're not going to worry about that. It's either going to be 1, 2, 3, or 4 cleavage planes. And for 2, 3, or 4, you're going to tell me what the angles are as well. At 90 or not at 90. No cleavage, it's going to have fracture, right? Here's some examples of different cleavage planes there. Your hardness, you're going to use the glass. Please be careful. Put it flat on the ground. You're going to scratch it. The mineral will be greater than 5.5 or less than 5.5. Color, you're going to make note of that. Streak, you're going to scratch on the streak plate, and you're going to record what the color is. The luster, and this is an important slide. I give you examples of all the most common lusters, okay? Vitreous or glassy, right? Pearly, it looks like seashell pearl. Resinous, it looks like dried tree sap. Silky, self-explanatory. Greasy, it looks like someone sprayed it with baking spray, like Pam, right? And earthy, it looks like it's covered in dirt. Okay? Pretty understandable lusters. Okay? If you can think of a better word for what you're looking at, put it down. There's also metallic and things like that, but that's easy to understand, right? If you can think of a better word for what you're looking at, please put it. It just needs to make sense. You can't make up a word. Flibbity gibbet is not an acceptable word for a luster. All right? Tenacity, the manner in which it breaks, or as you observe that it has broken. Brittle, that means that it kind of shattered. Malleable, that means that it's been molded like metal, like gold. Sectile, that means that it breaks into shavings, like wood. You know, when you snap a piece of wood, it breaks along the grain of the wood, and you can break it into strips. That's sectile. Flexible, it will bend, and then as soon as pressure is removed, it will return to its original shape. And then elastic, sorry, that's elastic. Flexible is when you bend it and then it retains that shape. And then there's transparent, translucent, and opaque. Does it effervesce under acid? Some minerals have birefringence, which means that when you put it on top of like lettering, it will double the image of that lettering to your eye. Magnetism, taste, all of these are different properties. Your process is going to look like this. Think of it like a flow chart. You're going to start with one property. Does it have crystal form? Then does it have cleavage? Then does it have this? Then does it have that? And you're going to go through the process of elimination to figure out what it is. Now, how are you going to tell what you're looking at? If you go to the Blackboard Lab 1 folder, those of you that have it open, go there now. You're going to notice that there is a folder there, a subfolder that says lab resources, and then in all caps, you will need to use these. Okay? One of the files in there is an Excel spreadsheet that says for labs 1, 2, 3, and 4. That is your master list. That's your best friend. That's going to get you through this semester. That Excel spreadsheet has every name and every property for every sample that you're going to see in this class. It copies the numbers next to those names are exact copies of the numbers on those boxes at the back of the room here. 1 through whatever. In the case of lab 1, 1 through 51 are 1 through 51 on that spreadsheet. So your process here is going to be doing what you did in class here today, using what you learned here in class today, and working with each other, hopefully. Please make groups. That makes it easier. You're going to be identifying the properties for each sample on the lab. And then after you have collected all those properties, you're going to the spreadsheet to compare what you found. We're looking for something with these properties. Let's go to the spreadsheet and find one that matches it, or at least comes close. If it comes close, let's go look at the sample at the back of the room and see if it's a match. Sound doable? Any doubts? Questions? For those of you doing this online, I know I just talked a lot about samples at the back of the room. You still have the same spreadsheet as everyone else, but instead of samples at the back of the room, in that Lab 1 resources folder, I have given you links to videos that I have made and published on YouTube, where I go through each one of those samples on the practice set there on that Excel spreadsheet, and I do all the tests for every single one of those. So instead of walking to the back of the room here and looking, you go to those videos and you look at the right number that you want to compare it to, and you see the properties that I collected there. Now I call those videos and what's on the Excel spreadsheet, I call it the practice set, because you can go there to compare before you even start the lab. If you're confused about what I meant by 3 directions of cleavage not at 90 degrees, go on the Excel spreadsheet find a mineral on there that has 3 planes of cleavage not at 90 degrees, and then either walk to the back of the room to see that box and see what it looks like, or look at the YouTube video to see what it looks like. Okay? It's called a practice set for a reason. The exercise set video for you, that's going to be how you do the lab. Those are the samples 1 through 24 you need to identify. All 24 of the samples you need to identify are out of the 51 practice set minerals. Okay? Now, for those of you here in the classroom, I have sets, actual physical sets of these minerals I'm about to hand out to you. Are there any questions before we stop? I end the recording and we go to lab time. No? Okay, I'm going to end this recording and we'll use the last 50 minutes of class for lab.